Okay, hey guys. I figured this would be easier than, some people may not be able to make it in today because of the weather or the, I guess, residual snow. So I figured this is the easiest option. Hopefully this is okay with everybody. Um, I am just going to finish up that PowerPoint that we started on Thursday. It's the first half of the physical environment chapter. We finished talking about like the combination of the Hadley cells and Coriolis effect. Definitely review that if you don't quite remember what's going on with those. The last part of this is really just about ocean circulation. So I'll go through these slides fairly quickly. I can answer any questions you have Thursday when we meet. There we go. I'll have an assignment that I'll talk about right at the end of this that will be due Thursday at the beginning of class as well. So we'll go over the answers to that. Okay, so ocean circulation, just like surface winds and precipitation, can have an effect on climate, which we don't often think of. So we're going to talk about how that happens. There are two main types of circulation in the oceans: surface currents and then deep ocean currents. I'll talk about each of these. I'll spend a little bit more time on the deep ocean currents. They're a little bit more complicated. Both are constrained by blank. This is where I'd ask you if I were in class, but no one's on the other end of this right now. So both are constrained by land masses or continents. Obviously, the ocean circulation, as you can see down here, the deep ocean circulation or the surface circulation is constrained by continents. Obviously, there's no ocean on the continents, so the water can't circulate on the continents. So that's pretty straightforward. Hopefully that makes sense. So we're kind of hemmed in ocean circulation by the big land masses, really. Ocean surface currents are mostly propelled by wind. So we're talking about kind of the upper few feet of ocean. Wind is what's driving most of that circulation that you see here. Some of these names might sound kind of familiar. The Gulf Stream hopefully sounds familiar since it kind of goes right by us here in the Southeast. The Humboldt Current is another big, really important current off the coast of South America that you may or may not have heard of. These are surface currents. They're propelled by wind. Not a whole lot else to say about those other than they are moving heat from one area of the ocean to another. So really quick, and I think this will come up when we talk about deep ocean circulation as well, but the Gulf Stream, that warm water coming from the tropics and subtropics down here, makes its way up into kind of the northern part of the Atlantic. That's why Great Britain, a lot of these northern European countries actually stay fairly warm. Deep ocean circulation accounts for that as well, but the Gulf Stream is bringing warm water from closer to the equator up into those northern reaches. So it's redistributing heat. The Pacific current is kind of doing the opposite, bringing cold water down the west coast of the country. So typically, if you've ever been in the ocean off of California, even if you're far south, it's really cold, right, compared to the Atlantic over here. So we've got warm water coming up. The Pacific coast has kind of cold water coming down from the northern reaches. Okay, so redistribution of heat is a big factor with the surface currents. The deep ocean currents, like I said, are a little bit more complicated. They are affected by temperature, which essentially affects the density of water, and I'll talk about that. And then salinity, so how much salt is there in the water. Both of these are going to affect how these deep ocean currents, since they're not propelled by wind, we're talking very, very deep, how these are driven around the world, mostly by water density and salinity. So some thermal properties of water. We're going to get into water in more detail, not the next chapter, but the chapter after that, I think. But this is just kind of what you need to know right now. Freshwater increases in density. This is a little bit weird. Freshwater increases in density as it cools down. So if you think about something increasing in density when it turns from a liquid to a solid, if you think of kind of basic chemistry, it's getting more dense as it's turning into a solid, right? Fresh water only gets denser until it hits 4 degrees Celsius. That's the magic number. Oh, whoops, sorry about that typo. And then density decreases. That 0 should be an end parentheses. So at 4 degrees Celsius, you get this weird cutoff. So density is increasing to 4 degrees Celsius. When the temperature gets below 4 degrees Celsius, the density then decreases, so it gets less dense. That's why ice floats on water. Ice is the solid form of water. It should sink based on what most other things do when they turn into solids. But ice, because it's 0 degrees Celsius, that's the freezing point, it's less dense, and so it floats. That 4 degrees Celsius is the magic number. We're going to talk about that actually in the next lecture, the physical properties lecture, the second part of this chapter, and what effect that has in freshwater systems. It has some major effects. So if we look at a simple kind of not well done table, apologies, for what happens to water temperature here on the left. So we're going from 20 to 10 to our magic number 4, and then below there to 0. And if we look at the density, you don't have to know these numbers. This is just showing you that density is increasing. So from 0.998 to 0.999 to 0.99997. This is the maximum density that water ever reaches. So this is the heaviest water. 4 degrees Celsius water is really heavy. It's going to fall below any water that is cooler than it, or warmer than it is. At 0 degrees Celsius, that density goes back up, 0.9984. Obviously not much of a difference, but this is what drives a lot of the deep ocean circulation. And then ice is a lot less dense. So water at 0 degrees Celsius before it's frozen, ice at 0 degrees Celsius is really a lot less dense than even, warmer water. That's why ice floats on any kind of water. Okay, so 4 degrees Celsius, that'll come up again when we talk about freshwater ecosystems. Salt water is a little bit different. It gets denser. It doesn't have this kind of flip at 4 degrees Celsius. It just keeps getting denser and denser until it cools almost to its freezing point. Salt water freezes at a lower temperature than fresh water. It freezes at negative 1.8 degrees Celsius. That salt in there keeps it from freezing at 0. So it just keeps getting denser until it freezes. And then when it freezes again, it's less dense. So no matter what, salt water or fresh water, if it's frozen, it's going to float. But liquid salt water, as it gets down to negative 1.8 degrees Celsius, continues to decrease in density. It doesn't have this weird flip at 4 degrees Celsius. Okay, so that's some basics about the thermal properties of water. To move forward, if we look at salinity, ocean salinity actually varies around the globe, and it depends on a number of factors that I'll talk about in just a second. Well, here I have them listed. It depends on evaporation, precipitation, and how much sea ice is melting nearby. How much water evaporates off the surface of the water, how much precipitation is gained into the ocean, and then basically how much fresh water from sea ice melting is gained, is going to affect the concentration of salt in the water. So you can see here, higher salinity is in that red color, lower salinity is blue. So if we're looking at, here's North America, here we are, we have a really high salinity in the Atlantic Ocean. In the Pacific Ocean, it's a lot less saline. It's still obviously very salty, but quite a degree less salty than we have on the East Coast here, off of the East Coast. Okay, so let's think about how these 3 factors affect salinity, because they'll affect them similarly in some cases, differently in other ways. So we're thinking about water salinity. That's just how much salt is there per unit of water. If water is evaporating, if we have evaporation off the surface of the water, salt does not evaporate, it stays there. So only water is leaving. That is going to increase the salinity of that body of water, that location of water. If there's more evaporation, the salinity increases. And we'll talk about this in relation in the next lecture again on Thursday. We'll talk about this in relation to like the Great Salt Lake is a good example, the Dead Sea, some really salty places. We'll talk about how evaporation is affecting that. So more evaporation, higher salinity. So it's a direct relationship there. Precipitation and sea ice melting are going to have the same effect. So they're going to go in opposite directions, basically, compared to what evaporation does. If there's more precipitation in an area, that means more fresh water is entering the system, entering the ocean. If more fresh water is entering the system, that means salinity goes down, right? So more precipitation goes up, salinity goes down. Same with sea ice melting. It's just a different source of fresh water. So sea ice is mostly fresh water. There could be some salt bound up in it, but it's mostly fresh water. If you have more sea ice melting, you have decreased salinity. You have a lot more fresh water coming in, which is why you see up here, these really cold areas, there's sea ice melting, and that's going to decrease salinity. Right around, I guess, kind of below the equator here, but in these warmer areas, you get a lot of evaporation because of the heat and increased salinity. Okay, so definitely know if I asked you examples or gave you some examples of differences in evaporation or precipitation or sea ice melting, know how that would affect an ocean's salinity or an area's salinity. Okay, and then we have, if we combine both of these ideas, the temperature and the salt content, we have what's called the thermohaline circulation, or the Great Ocean Conveyor Belt, which you may have heard of. Thermo refers to temperature, haline refers to salinity. So temperature and salinity are driving this huge conveyor belt that you can follow around the world, around the major oceans. And you can see sort of the effect it has. So this is going to affect temperatures in different areas. So we see the Gulf Stream here. The Gulf Stream has a surface circulation component as well as a deep ocean current component. So the Gulf Stream is really important. I have a video here that I'm going to show you in just a second that'll talk about how this affects some northern latitudes up in kind of northern Europe here. But you can see obviously the red arrows, that's warm water. It'll then sink down, or cold water will come up, and you have a cold circulation water flowing down kind of south near Antarctica. So cold, salty, deep current. And then you have this warm kind of surface water. So you have this change in where the water is. And if it's cold and low, it can eventually come up and it'll warm up over time. And it's hard to explain that with just this diagram. So I think this video does a really good job. So I'm going to stop sharing this right now and then go to the video. Share that with you guys. And this will explain that thermohaline circulation. I think it's mostly focused on the Gulf Stream because I think it's another English video. Okay, here we go. Hopefully you can hear this.
The ocean conveyor belt and the Gulf Stream. Ocean currents have a direct influence on our lives. They determine our weather, our climate, and much more. The ocean currents and wind systems transport heat from the equator to the poles and operate like a large engine for the global climate. In the oceans, there are numerous currents. The so-called ocean conveyor belt is very important for our climate. This term describes a combination of currents that result in 4 of the 5 global oceans exchanging water with each other. They form a worldwide circulation system. The conveyor belt is also called the thermohaline circulation, with thermo referring to the temperature and haline to the salt content of the water. Both determine the density of the water. While the masses of water may be moved in part by wind, primarily the different densities of the global oceans are responsible for their movement. Warm water has a lower density and rises, while cold water sinks. The water's density also increases with a higher salt content. At the equator, the heat from the sun is especially strong, resulting in a lot of evaporation and thus a rise in the water's salt content. That is where the Gulf Stream begins. The Gulf Stream is very important for the European climate. Its length of 10,000 kilometers makes it one of the largest and fastest ocean currents on Earth, and it's very warm. At roughly 2 meters a second, it brings up to 100 million cubic meters of water per second towards Europe. A constantly blowing wind, the southeast trade wind, drives warm surface water to the northwest into the Gulf of Mexico, where it heats up to 30 degrees Celsius. The turning of the Earth and the west winds then direct the Gulf Stream towards Europe and split it up. One part flows south, another east to the Canary Current, and a third part flows north, where it releases a lot of heat into the atmosphere as the North Atlantic Current. The water becomes colder there. Its salt content and density rise on account of evaporation, and it drops down between Greenland, Norway, and Iceland. There we also find the largest waterfall on Earth, the so-called chimneys, roughly 15-kilometer wide pillars with water falling up to 4,000 meters. 17 million cubic meters of water per second, or roughly 15 times more water than is carried by all the rivers in the world. This creates a strong maelstrom which constantly pulls in new water and is the reason that the Gulf Stream moves towards Europe. Countless species use the Gulf Stream as a means of transport on their trips from the Caribbean to northern areas. But it doesn't just bring us animals. An enormous quantity of warm air also comes with it. In order to produce the same heat which it brings to the shores of Europe, we would need 1 million nuclear power plants. That's why we also call the Gulf Stream a heat pump. Without it, the temperature would be significantly colder here, at least 5 to 10 degrees. Instead of lush fields, we would have long winters and sparse ice-covered landscapes in Europe. In the last few years, scientists and pundits in the media have repeatedly expressed the fear that the Gulf Stream could come to a standstill due to climate change. Because if the polar caps actually melt, the salt content in the water off Greenland would fall, as would its density. The North Atlantic Current would no longer be heavy enough, and so it wouldn't sink as usual. In the worst case, that would bring the Gulf Stream, our heat pump, to a stop. Some climate experts also assume that climate change could compensate for this effect. We know that it can be normal for the climate to change by looking at the development of the Earth over the last few million years. There are ice ages and warm periods. In the last ice age, a gigantic flood of melting water crippled the heat-bringing North Atlantic Current, covering the northern hemisphere in ice. Scientists have different views on the impact that climate change will have on the global ocean conveyor belt. But one thing is clear: when the climate changes, then the complex system of ocean currents and winds, which has remained fairly stable since the last ice age, will change in ways that we don't yet understand.
All right. So hopefully that kind of helped explain a little bit more what I was talking about with the, I don't think I mentioned the salinity effect on density, sorry, but more salt in the water is going to increase density as well. So cooler water, as well as, until that 4 degrees Celsius cutoff, as well as more saline water is heavier. So yeah, like I said, that's what's bringing a lot of heat to Northern Europe. And that's why people in Northern Europe are also particularly concerned about climate change and how that might affect the Gulf Stream part of that in particular. All right, let me share the PowerPoint again. All right, so that's the general idea behind these deep ocean currents and how it's moving heat around the globe. So this temperature and salinity change, like it just showed in that video, leads to these vertical movements of water between the surface and the deep oceans. So cold water, cold, salty water is going to sink. Warm, less salty water is going to rise up to the top. The idea, there's downwelling and upwelling. They are pretty self-explanatory. Downwelling is where you get a lot of water, like that big waterfall up near Greenland that they mentioned in that video, bringing a lot of warm water down to the bottom as it cools and becomes more saline. So downwelling is the falling of surface water to the bottom, to the deeper depths of the ocean. That's bringing some heat with it. Some nutrients potentially, but generally the movement of water as it cools going downward. That's downwelling. I'm not going to spend a lot more time talking about downwelling. The opposite is actually a lot more ecologically interesting and important. So I'll spend a couple of slides on that. And that's what your assignment that I'll have posted is about. It's about upwelling. So downwelling, the falling down of denser water to deeper depths from the surface. Upwelling is the opposite. So it's cold, nutrient-rich water moving up to the surface. And this happens in large part because of winds on the surface of the ocean. I won't go into the details of this longshore wind. Typically, upwelling happens near the edges of continents. So you get a lot of this, the longshore wind is basically going to drive, so longshore wind along the edge of the continent is going to drive a lot of this cold, nutrient-rich water. So the nutrient-rich is the really important part here. It's going to drive it up to the surface. So it's going to sort of keep getting pulled up as water on the surface gets pushed away from the edge of the continent. So cold, nutrient-rich water moving up to the surface is upwelling. And upwelling is responsible for a lot of the productivity that we see along certain edges of continents. So a lot of the ocean productivity, and not even just along the edges of continents, you can see out here, there's a lot of productivity, is happening because of upwelling. So I'm going to describe what these colorful figures are showing. Chlorophyll A concentration. So this is basically, if you guys remember anything from Bio 2 or maybe another class, even Bio 1. Chlorophyll is what plants have, right? That's how they photosynthesize. That's the pigment that absorbs the sunlight. So the more chlorophyll, which is any of the warmer colors here, that's more chlorophyll A concentration. So where you get these greens and then the reds, especially the reds and oranges along the edges of these continents, that's a lot of chlorophyll. And chlorophyll in the ocean is mainly due to algae. So when you see that, think, okay, these warm colored areas, lots of chlorophyll, that means a lot of algae. That is because, and I would normally have you guys discuss this, but since we're not in person, I'm just going to explain what's happening here. It's a little less exciting, but as you get a lot of that nutrient-rich water upwelling, so you get a lot of nutrients coming up to the surface of the water, that's where the algae live, right? Because the algae need sunlight. Algae are at the surface of the water. They still need nutrients. Those nutrients coming up from the bottom, from that upwelling event, it's going to feed those algae the nutrients they need, and they can flourish. So upwelling drives a lot of the productivity. And by productivity, we'll get into the specific details of that in another chapter. But here I just mean how much biomass there is. And particularly in this case, we're talking about biomass of algae. So how much algae there is driven by upwelling. So you get more of that nutrient-rich water, you get more algae, and then potentially even from there, you get biomass from herbivores that are eating the algae, omnivores, carnivores that are eating those lower trophic levels as well. So you get this kind of cascading effect. When you have a lot of upwelling, a lot of nutrients, it just allows for a lot more biomass, a lot more animals and plants to develop in that area. Okay, so upwelling is very important. This brings us to, well, the end, as well as the assignment that I will post on Canvas, and it will be posted by the time this video is available. So it should be up there at this point, talking about upwelling and salmon abundance. So this is not specifically algae oriented. We're looking kind of higher up the trophic level, specifically in the Columbia River in Oregon. I'm not going to go into detail about what this is showing. The goal of the assignment, if you go to the assignments page, you'll find upwelling and salmon abundance assignment. You are going to interpret what this graph is showing. So this is similar to a question I would ask on an exam to interpret the data that is being shown. I'm not going to go into detail about what this is other than Chinook or salmon. It's a species of salmon, which you can see here. You can read the figure caption to help explain what the graph is showing, but I want you to explain it in your own words. That's the first question. And the second question on the assignment deals with the fact that, this 2 years earlier idea. So why are they looking at upwelling from 2 years prior? That's the second question, something to think about. The only additional thing I'll say here on the x-axis, since it's not super clear, this upwelling index anomaly. Just think of that as the numbers get bigger and there's more upwelling, okay? It's just a kind of a generic index for understanding upwelling. So yeah, as you go to the right on the graph, the upwelling increases. And these are, anyway, you can read the figure to interpret more of that. You don't have to worry about the R-squared and the p-value. If you want to explain that, you can, but don't feel like you have to. Upload that by, like I said, the start of class on Thursday. So by 9:30 on Thursday morning, upload your answers to Canvas. You can handwrite or you can type in the answers. I don't really care how you do it. You can upload a picture of your handwritten answers if you want to. And that wraps up everything I need to say for this PowerPoint. Here's the overall learning objectives, terms, and concepts. And with that, we are done with the first half of the physical environment. We're a little bit behind, so I'll try to catch up on Thursday and Tuesday of next week. Okay. Let me know if you have any questions. I'll kind of open up at the beginning of class on Thursday. I'll open up the floor to any questions that you have about this stuff that I went over, since I wasn't able to answer them in person at this point. Okay, don't stress too much about the assignment. I'm mostly just trying to get you to think about data and try to understand sort of what's going on without me explaining everything, and kind of get used to the kinds of questions that I ask on exams. Okay, cool. I'll see you guys on Thursday.